Hello and welcome to MATLAB programming for numerical computations. We are in the second half of module 3. In this part, we are going to cover numerical integration. In today's lecture, we are going to cover a range of integration formulae known as Newton-Cotes integration formulae. Numerical integration is primarily just finding area under a curve. For example, if a curve is f of x, then integral f of x dx from a to b is nothing but this shaded area that you can see between the points a and b lying below this curve. So if we were to use trapezoidal rule for this particular example, what trapezoidal rule amounts to is calculating the area under this trapezoid. The trapezoid is formed by joining the dots f of a with f of b. As you can see in this cartoon over here, if we apply a single application of the trapezoidal rule, we are going to be fairly inaccurate. The results are not going to match closely the actual values of integral. So trapezoidal rule basically, as we said, is just joining two dots with a straight line and finding the area under that. Instead, we can take 3 points, the point over here, the point over here, and the midpoint, join them. 3 points we can join with a second order curve, and the area under that curve is going to give us what is known as Simpson's one-third rule. So Simpson's one-third rule is obtained by joining point A, point B, and the midpoint between A and B. These 3 points are joined by a curve, and what we obtain is known as the Simpson's one-third rule. So the step size h in Simpson's one-third rule single application is half of that of the trapezoidal rule. The next Newton-Cotes formula can be obtained by connecting 4 points within this region. So if I just go back, so we had in trapezoidal rule these 2 points, in Simpson's one-third rule 1 more point at the center. In Simpson's 3/8 rule, what we will have is these 2 points and then 2 more points that are equally spaced. So if we take this point, if we take the next point at h by 3, the third point at 2h by 3, and the fourth point at this guy, okay, and if we were to connect all of these through a smooth third order curve, the area under that curve will give us Simpson's 3/8 rule. In a single application of Simpson's 3/8 rule, the step size h is going to be b minus a divided by 3. So the step size in Simpson's single application of Simpson's 3/8 rule is 1/3 of the step size that we use in the trapezoidal rule. We can of course have higher order formulae. So instead of 4 points, if we were to have 5 points and connect them with a 4th order curve, 6 points connecting them with a 5th order curve, so on and so forth, will give us higher and higher order Newton-Cotes formulae. Okay, so the trapezoidal rule integral from a to a plus h of f of x dx is going to be h by 2 f of a plus f of a plus h. What this means is it's an area under this trapezoid. So it's this height multiplied by this height plus this height multiplied by this base divided by 2. That's what the area under a trapezoid is. The Simpson's one-third rule is given over here is h by 3 multiplied by function value f of a plus 4 times f of a plus h plus f of a plus 2h. That's what the one-third rule is going to give us. F of a plus 4 times f of a plus h plus 1 times f of a plus 2h. The whole thing multiplied by h by 3 will give us the Simpson's one-third rule. And Simpson's 3/8 rule, for the sake of completeness, I'm just showing over here. We won't cover Simpson's 3/8 rule in this lecture. So these are the Newton-Cotes integration formulae. To summarize the formulae and the local truncation errors, the trapezoidal rule formula is this. The local truncation error is the h to the power 3. So the trapezoidal rule from the local truncation error, single application of trapezoidal rule, is h to the power 3 accurate. Single application of Simpson's one-third rule is h to the power 5 accurate. So it's significantly more accurate than the trapezoidal rule. Simpson's 3/8 rule is also h to the power 5 accurate. As a result of this, usually Simpson's one-third rule is more popular than Simpson's 3/8 rule, And for the simplicity of application, the trapezoidal rule is also very popular. Let's take up an example and solve that in MATLAB. The theoretical aspects of this were covered in Module 6 of Computational Techniques. Specifically in Module 6 Part 3, what we are going to focus on is we are going to calculate integral from 1 to 2 f of x fx dx using the trapezoidal rule and the Simpson's one-third rule. Integral for this f of x is given over here. So let's go to MATLAB, okay, and do this problem. Edit num integral. Of Newton Cotes formulae. F of x equal to, okay, so let's say a equal to 1, b equal to 2, trapezoidal rule, 1/3 rule. True val is going to be equal to x minus x square by 2 multiplied by x ln x. So b minus b squared by 2 plus b multiplied by ln b, b multiplied by log b. If you recall, log gives the natural logarithm. So you can do help log. If we wanted log to the base 10 instead, we would use the command log 10. Okay, so this minus a squared by 2 plus a into log a. That's going to be our true value. Okay, so for trapezoidal rule, single application. H is going to be nothing but b minus a. Okay, I trap is going to be equal to, let me just put underscore over here, I trap is going to be equal to h by 2 multiplied by fa plus h equal to h by 2 multiplied fa plus fb, and we need to put this inside a bracket, okay, where fa is nothing but 2 minus x plus ln x calculated at a. So it's 2 minus a plus log a, okay, and fb is nothing but 2 minus b plus log b. Okay, so let's save this. ERR trap equal to ABS true val minus I trap. Okay, let's uncomment both of these, save this, and let's run this and see what results we get, whether we get an error or we get the results. So let's run this. It runs properly and the error is of the order of 0.04. So this error is quite substantial, as we had seen in the cartoon over here. The single application of trapezoidal rule sometimes can be very, very inaccurate. Okay, so it's a single application of, so as we have seen over here, the true val of the integral is 0.8863, whereas the approximate val from trapezoidal rule is 0.8466. Yeah, so let's go over here. What we want to do is something that we had done earlier in the previous lecture. What we want to do is, instead of calculating the function values in line like this, we want to give a different function to calculate f of x. Okay, so let's create a new function called my fun integral. So function fval equal to my fun int x fval equal to 2 minus x plus ln x, 2 minus x plus log of x end. And we save this as my fun int, and fa is nothing but my fun int a, and this guy is nothing but my fun int b. Okay, we save this and run this and see what we get. We should get, if everything runs fine, we should get the same values as before, and that's exactly what we get. The error in trapezoidal rule is 0.04 and the integral value is 0.847. That's exactly what we had got earlier. Okay, in Simpson's rule, h is b minus a divided by 2. That's what h is going to be. Okay, and I sim is going to be h by 3 multiplied by f1, so fa plus 4 times fa plus h plus fa plus 2h, or we can say f1 plus 4 times f2 plus f3. So let's just do that. F1 plus 4 times f2 plus f3, right? Okay, what is f1? f1 is nothing but function f calculated at a. What is this guy? F calculated at a plus h, and this guy is f calculated at a plus 2 multiplied by h. Okay, okay. What is the name of the functions that we created? The name of the function that we created is my fun int. So let me just replace this with my fun int. Again, f I will replace with my fun int, and this f also I will replace with my fun int. Okay, that will give me isim, and err sim is nothing but abs trueval minus I sim. Display results, and we should be able to get the results more easily. So the errors using trapezoidal rule is 0.04, but the error using Simpson's 1/3 rule is about 4.5 into 10 to the power minus 4. So as you can see, the Simpson's 1/3 rule is significantly more accurate than the trapezoidal rule. Okay. So this is what we have seen. The LTE in Simpson's 1/3 rule is h to the power 5, whereas the local truncation error in trapezoidal rule is h to the power 3. Okay, and therefore in this particular example, it turns out that the Simpson's 1/3 rule gives better results than the trapezoidal rule. Okay, so next what I'm going to do is I'm going to take this trapezoidal rule and I'm going to calculate the value of trapezoidal rule, the integral using the trapezoidal rule for different values of h. So we'll start with f of a, okay, and f of a plus h, we will calculate this for different values of h. That means fb will be calculated for different values of h. Again, we are restricting ourselves to single application. So let's go to this num integral, drop down the save and click on save as num integral 2. I will call this. Okay, we don't want Simpson's 1/3 rule. A is going to be this, h is going to be 1, and b is going to be a plus h. Okay, and this is going to be our true value. We don't need this. Now what I'm going to show is, let's say we have this particular code, snippet of code over here, how we can make this code a bit more streamlined. You have this FA over here, okay? We can just delete this FA and replace it with what existed over here. So just highlight it and drag and drop. Okay, same thing over here for FB also. Delete FB, highlight this part, drag and drop over here, delete these two guys. Okay, so let's save this. Let's clear all, CLC. and let's run this for h equal to 1. Okay, the error trap that we get is 4 into 10 to the power minus 2. Okay, I will uncomment this part. Okay, now let us decrease h by 1 order of magnitude and take our h to be 0.1. Okay, our trapezoidal rule is h to the power 3 accurate. What that means is decreasing h by 10, we should decrease the error by 1000. So the error should decrease by a factor of 10 to the power minus 3. So let's run and see what the error we get now. By running this, you can see that the error has dropped from 4e minus 2 to 7e minus 5. So this is an almost 3 orders of magnitude. This is actually a 3 orders of magnitude drop. Let's drop this further to 0.01 and let's run and see what we get. When we run this, we further see a 3 orders of magnitude decrease in the error. Let's drop this even further and see what we get. Save, and we will see 3 more orders of magnitude decrease in the error. Error went from 8.2e minus 8 to 8.3e minus 11. So as we decrease the step size by a factor of 10, the error improves by a factor of 1000. The error goes down by a factor of 1000, and that is because trapezoidal rule is h to the power 3 accurate. So this particular slide itself summarizes what we have covered in the lecture today. What we have covered is trapezoidal rule and Simpson's 1/3 rule. What we have seen is trapezoidal rule is h to the power 3 accurate. What you may want to test as a practice problem is to verify that Simpson's 1/3 rule is h to the power 5 accurate. I'm not going to do that in the video lectures because it simply follows the same procedure that we have done with the trapezoidal rule. Okay, and with that, I come to the end of this lecture. This brings us to the end of lecture 3.4, and I will see you in the next lecture. Thanks and bye.